So the total length is ceiling log n plus 1 plus ceiling log n choose k. Yep.
So we are transmitting the number of k's plus the possibilities of having that many k's.
Right, so once I know k, I know that, for instance, once I know k equals 1, I know that the code word must be one of these 5.
But here you say code word of k code.
Yes.
But is this the code word log n choose k? It's the possibility of code words.
That's the number of code words in
Not
the kth code.
Not the code word itself.
What do you mean?
In the explanation of C, it says code word of kth code.
Yes.
So we are not transmitting the code word, but the total possibilities, number of possibilities for that code word. Am I missing?
What I'm asking is, okay, this is the code word we transmit. What is the length of that code word? So, what's...
Oh, length, I'm sorry.
Yes.
Yes, sorry.
So I have 5 code words here. I need 3 bits to represent them. So that's ceiling log 5 choose 1.
So this was L, so I'm sorry.
Okay. We can rewrite that. We can get rid of the ceilings and say this is less than or equal to log n plus 1 plus log n choose k plus 2. So the ceiling, the result of ceiling can be no more than 1 greater than this. So basically I'm collecting the 2, I'm eliminating the 2 ceilings and saying that in total it can't be any more than 2 greater than that. All right, there's a lemma which we will not prove. Define h of p as the binary entropy function where h of p, basically it's the entropy of a binary source where p is the probability of 1. So what would that be? That would be p log 1 over p plus 1 minus p log 1 over 1 minus p. So if p was the probability of 1, this would be the entropy. So it's just some function of p. If that is true, then we have the following. N choose k, 2 to the minus n h of k over n is greater than or equal to root n over 8k n minus k, and is less than or equal to root n over pi k n minus k. So the sandwiching in the denominator over here we have 8, and in the denominator over here we have pi. So that's where the sandwiching comes from. Or I guess that's the difference between these two terms. Okay, how do we use this to talk about this? Well, what we really want is entropy. We want to talk about length in terms of entropy. And what we have here is n choose k. So what I'm going to do, what I want to know is I want to have a lower, excuse me, this is already an upper bound on length, right here. So if I have a further upper bound on length, I'd like that to employ entropy somehow. So, I can write length less than or equal to log n plus 1 plus log n choose k plus 2. So here's something I can do. I can notice that log of n plus 1, as long as n is greater than 1, as long as this argument is greater than as long as n is greater than 1, which it is in general, log n plus 1 is less than or equal to log n plus 1. Basically, I'm just taking the 1 outside, and that's because log looks like this, greater than 1. And there's, if at any point I take that value and add 1, so that there's the tangent line that increases, and it's always below that line. Okay, so that's helpful. That means this is less than or equal to log n plus log n choose k plus 3. Now, I want to use this. I'm going to use the upper bound. So therefore, n choose k, if I multiply through by 2 to the n h k over n, n choose k is less than or equal to 2 to the n h k over n times root n over pi k n minus k. I can plug that in here. This is less than or equal to log n plus log 2 to the n h k over n root n over pi k n minus k. Now it's just manipulation. So I've already used this, let's erase that. This is equal to log n plus, okay, log of this times that is log of this plus log of that. Log of 2 to the n h k over n is what? n h k over n. Plus, okay, log of root something is equal to 1/2. So in other words, log root x is equal to 1/2 log x. So I can take this square root out and write 1/2 log n over pi k n minus k plus 3.